Welcome back to ECE 501B. Today is 1 week prior to exam number 1. Exam 1 will be the next time, or in a week from now. We will meet again on Monday, and that's when homework 4 is due, and that better be assigned shortly. I need to make sure and get that on D2L. Exam number 1 review session is Monday, I think, is what we agreed on. I'm not sure if we have the classroom. They're being a little ornery, but we'll see if we can have that right after we finish our lecture on Monday. Today what I want to do is very quickly comment on the main features of Chapter 4, which is dealing with polynomials. You're sort of on your own to read that material. We'll then today begin Chapter 5, and I'm hoping that I can still go back and record maybe a little bit more material for Chapter 3 to finish up Chapter 3, and I'll put that in Unit 3's section on D2L. That's the plan when I get a free minute or two. So we'll start Chapter 5 with some examples showing some properties and the existence of eigenvalues and eigenvectors, what that sort of means, trying to get us comfortable with that. Then we'll get into the more background development, starting with the book material in Axler, after we've sort of motivated or given you maybe something a little more concrete to be thinking about relative to eigenvalues and eigenvectors. In Chapter 4, it's dealing with polynomials. Just to get us all on the same page, I've simply written down a representation of an mth order polynomial with the m plus 1 coefficients, a sub 0 through a sub m, and those coefficients could be coming from our field F, which says, oh, they could be real or they could be complex. And that could be our polynomial P as a function of this variable Z, which also is coming from that field of real or complex numbers. One of the results that is key is that a polynomial has a root if we can factor out a linear factor z minus lambda from the polynomial p of z. If we can't factor out a linear factor, then we may not have a real root in that polynomial, p of z. So it's critical what the field of numbers is where we're drawing these scalars from, whether it's the real number line or the complex plane. And that makes a difference on whether or not these polynomials indeed have roots coming from or living or belonging to those fields, real or complex. And maybe we'll see that today. I hope we do a couple of times maybe in some of the material in Chapter 5. Another key result is theorem 4.7. Obviously, it's key if they call it the fundamental theorem of algebra. And that is that, and now you have to realize that this field of numbers is complex, but that fundamental theorem of algebra states that every non-constant polynomial, so it's a polynomial that's more than just a sub 0, it's a sub 0 plus a1z, it's at least that elaborate or complicated. Every non-constant polynomial with complex coefficients has a root, and that's key. But the key is that we now have this field of numbers, or these scalars, coming from the complex plane. If they come from the real line, this field of numbers, then we're dealing with a slightly different animal, which is theorem 414. In that case, we have a polynomial that can be factored, but it may not be factorable into linear factors. We may be able to only factor as far as factors that are quadratic in structure, meaning we may have little m factors that are linear, and so these lambdas are real. The c is real. All of these things belong to the real number line, but now there may be pieces of that polynomial that we can't factor into pieces that contain real numbers. If we needed to factor x squared plus alpha 1x plus beta 1, we couldn't do that with real number factors. We would have to enter the complex setting or the complex field to obtain factors. Or what we're saying is when we set these quadratics to 0, we can't find real values for x that cause those to vanish or to equal 0. These factors, that's a capital M, so 1, 2, up to capital M of those factors do not possess real roots. And that's theorem 414. I would just say look at chapter 4 and make sure that you're comfortable with these concepts, because those are going to be relied upon now that we're into chapter 5. But we won't really explicitly deal too much with polynomials and chapter 4 materials specifically or directly. We'll just use that information from chapter 4, which now allows us to jump immediately into chapter 5. And in chapter 5, now we are playing with what we will spend most of the semester dealing with, and that is working with operators. A matrix representation of an operator we might label as an A matrix, which is then belonging to this set of matrices that are n by n, meaning the row dimension and the column dimension are the same, which says that A is a square matrix. That's now what we're dealing with if we're talking about a matrix representation of these operators. The operators, which is the last part of chapter 3, is where that took us, and that was saying we have these vector spaces that are isomorphic, that we now have this mapping, and if it has an inverse transformation, then, or if an inverse exists, then we do have these two vector spaces are isomorphic. Now that we're dealing with these operators, the concept in chapter 5, I think is clear from the title, is now we're dealing with eigenvalues and eigenvectors. And I might just write that a lot of times as AX, capital A, X is equal to lambda X. These X's are vectors. It's the same vector. That's a vector. And its coordinates, or its elements, those scalars that make up that vector that's maybe n by 1 in terms of a column vector. This is a vector with coordinates in our field of numbers f. And lambda is a scalar from this field of numbers f. And actually the elements in the matrix, all of their elements are in f. So f is typically either the real number line or the complex plane, or numbers from the complex plane, or these fields of reals and complex numbers. If this equation exists, or if an x if we can find a vector and a scalar that satisfy that relationship, ax equal lambda x, again, I'm just sort of giving you a motivation and a big picture so that we can dig into the chapter a little bit with a little bit better understanding when we start talking about the background of chapter 5. If an x and a lambda exists, then x is what we will call an eigenvector. And lambda is an eigenvalue. And we'll show cases where if we're dealing with the field of real numbers, this x's and lambdas may not exist for a given A matrix. But what this is telling us is there's something pretty special happening here. You're taking this matrix that's n by n and operating on a vector, and after it does that transformation, it takes that vector and it basically stays on that vector. That's really what this is saying. It's just scaling along that same direction. So you have a direction in some n-dimensional space. You operate on it by this linear transformation, this matrix, and it maps you right back onto that same vector. That's what this eigenvalue, eigenvector equation is telling us. Let me see if I can sort of say that in words a few times. The operator, that's that matrix A, the operator takes a vector and maps back into a scaled version of, let me say, of that same vector. Or what I was trying to get you to visualize, suppose that this vector x is an element of R3. Or now you could be thinking XYZ, this space, this three-dimensional space. Then the operator's action keeps the point. So if we started at a point x, and that's what this vector is representing, x, we're starting at a point x, then we operate on that point by this linear map A, and now what that does is it just takes us back to a line that contains that point, that original point. The operator's action keeps the point in 3D space on the same line as it started. Meaning you have a point, you operate on it by this 3 by 3 matrix, and it maps back onto a line containing that same point. So you're staying on that line. That line is sort of invariant with respect to that map. You're not varying from or off of that line. Let's look at some examples, and then we'll get into the background. But I think it's helpful to sort of see some examples of what's what we're talking about before we even start talking about invariant subspaces, etc. Suppose that I give you, and now to make it as maybe clean as possible, let's start with 2 by 2 matrices. And I hope that you're comfortable with this matrix A1. A1 is a diagonal matrix. This is about as easy of a matrix as you can get. It's basically going to start looking or acting almost like a couple of scalar problems. They're disconnected or independent. A1 is a diagonal matrix. And this diagonal characteristic, or the fact that it is diagonal, makes it very special, or maybe nice. All right, let's see why this is so special, or why this is such a nice matrix. Let's now just look at, suppose that we picked a vector, and maybe we said, let's just start with something easy. Suppose that vector lies on the x-axis. Suppose v1 lies on the x-axis. Or now I'm saying, suppose we let v1 be this vector 1, 0. And now what happens when we operate on that vector v1 with the matrix A1? Well, we can do that operation, and based on what we talked about last time, what is this column vector going to do relative to all of the columns in the A matrix? It's just going to pull off the first column, isn't it? It's just going to say, I just want to take 1 times the first column, and that's what the result is going to be. This now becomes then the first column of the A matrix. And if we look at that, we could actually factor out a -1, and we in fact get back that x-axis that we started on. So we now have A v1 is equal to a number, lambda v1, where this is now our input vector. And -1, 0 is the output, but that's just a scaled version of the input. It's scaled by this scalar -1. So our resulting output vector stays on the x-axis, with the output being scaled. The output is scaled by -1 from the input vector. Meaning we've basically just found an eigenvector associated with that matrix A, because that's what we said an eigenvector does. When it's operated on by that matrix, we just get back to that original vector. What about if we tried a different vector? Suppose we picked a second vector the x-axis worked so well, let's try the y-axis and see what happens with that. And I hope you can almost, or you can anticipate what's going to happen here. V2 is now 0, 1. If we have A1, V2, what's that column doing to the A matrix? Or the columns in the A matrix? It's going to just extract or retain the second column, which is 0, minus 2. And that's just a scaled version of what we started with. And it's scaled by minus 2, which was actually on the diagonal to begin with. This output vector stays on the y-axis, and it's scaled by minus 2. If we make some general comments from this sort of trivial example, we can say that the initial vectors that we started with were actually eigenvectors. They behaved like what we said an eigenvector needs to behave like. The x-axis and the y-axis, those are eigenvectors for this particular example. And the scaling quantities, the minus 1 and the minus 2, were actually eigenvalues. Our A matrix was a real matrix that was 2 by 2. With our notation, that's n is equal to 2. And that 2 then says that we could have as many as 2 eigenvalues, and we did. We could have as many as 2 eigenvectors, and we did. The scalings were real. They weren't complex numbers. We stayed right on those original vectors, and A was that special matrix. It was diagonal, which actually allows us to conclude that the eigenvalues are indeed those diagonal entries or diagonal elements. The eigenvalues were the diagonal elements. What about another example? Suppose we say A2 is minus 1, 1, 0, minus 2. This matrix also has a specific structure or a particular structure. It's referred to as upper triangular. It has non-zero entries above the diagonal, but everything below the diagonal is 0. So we call that upper triangular. And we can simply quickly make some comments relative to A sub 2. With this upper triangular, we can still immediately find or identify the eigenvalues. They're on the diagonal again. The eigenvalues are minus 1 and minus 2. So if I ask you on the exam to find the eigenvalues of a matrix and I give you a diagonal matrix, that's a gift. If I give you an upper triangular matrix, that's a gift. If I give you a lower triangular matrix, that's a gift. The eigenvalues are on the diagonal. In this case, you would maybe need to show this, but lambda 1, if it's equal to -1, it has a specific eigenvector associated with it. And its eigenvector, let's say v1, is proportional to the x-axis. It could be some scaled version of this. We don't have, I mean, there's all sorts of eigenvectors. They're just scaled cousins of one another. You could say the eigenvector was 2, 0, and that would be an eigenvector. 10, 0 would be an eigenvector for this particular system, or A matrix. Likewise, if we looked at A sub 2, so you just need to be in the span of that. All your eigenvectors share the same span. V sub 2, in this case, the eigenvector for -2 is actually -1, 1. It's not the y-axis, because this was not a diagonal matrix. We had a little bit more structure in the matrix, and now the eigenvector, and you could show that, you could prove that to yourself if you wanted to. And so let's just do that. Let's verify that indeed what do we need to show? We need to show that A sub 2, V sub 2 gets back to a scaled version of V sub 2. A sub 2 was -1, 1, 0, -2. We hit that with -1, 1. That says we take -1 times the first column and add that to the second column. Or we now have -1 times -1 and 0. That's the first column scaled by -1. And we add the second column. But in fact, that's -2 times -1, 1. No. What am I doing? Is that okay? So I didn't do my notes right. But this, I think, is okay, right? So this is now some scalar times the same vector v sub 2 that we started with. Is my algebra okay? So that now verifies that indeed v sub 2 is an eigenvector associated with the eigenvalue -2. Let's look at another example. I just kind of went crazy with examples, so you'll have to just bear with me, but hopefully these will start getting a little bit more interesting. Suppose that I now have a B matrix that's -3/2, -1/4, -1, and -3/2. Now, if we restrict ourselves to only dealing with real eigenvalues, it may be that a matrix may not have n real eigenvalues. And so for this 2 by 2 matrix, unless you see it directly or if you calculate it, it may not be that it has any real eigenvalues. It may end up with a characteristic polynomial that can't be factored into real roots. That's what we're meaning. This is a 2 by 2 matrix. We should expect that we'll find a quadratic formula for the eigenvalues associated with that matrix, and it might be that that quadratic formula or quadratic equation doesn't have real roots. If we're interested in this as an eigenvalue eigenvector problem, then we're after or we're trying to see if an x and a lambda exist that satisfy this, where all the entries, all the elements in the x vectors, or the x vector and the lambda, those are real. We're wanting to see if that's true. To do that, suppose that we now give this x the coordinates x sub 1 and x sub 2. Again, you have to remember what the context is. Now that x sub 1 is not a vector, it's a scalar, and x sub 2 is a scalar, and those are our coordinates in that vector x. Is that okay? Sometimes we use x1 to be a vector. Sometimes we use x2 as a vector, but now we are not. But if we now use this structural definition for x, bx equal lambda x says that we now have minus 3/2 minus 1 in the first column, minus 1/4 minus 3/2 in the second column, x1, x2. That's supposed to equal some scalar lambda times that vector, which is lambda x1, lambda x sub 2. That's just bx equal lambda x. We're trying to now see, do lambdas, real lambdas, exist that allow this equation to be true? If we look at the first row, we can multiply that out and we see we have minus 3/2 x1 minus 1/4 x sub 2 is equal to lambda x sub 1. The second row says that we have minus x1 minus 3/2 x2 is equal to lambda x sub 2. If we pull all of the terms to the left and combine coefficients, we can then rewrite this as minus 3/2 minus lambda times x1 minus 1/4 x2 is equal to 0. If we do the same thing here, we have minus x1 plus a minus 3/2 minus lambda x sub 2 equals 0. And now I'm actually wanting to solve these for lambda, or find a formula for lambda. So if I take this one and solve it for x1, if I push x1 to the other side, I have x1 is now minus 3/2 minus lambda x sub 2 is is there. I can just stop. Okay, and let me call this equation here A, and let me call this equation B. And let me now substitute B into A. I'm going to get rid of x sub 1 in that first A equation, and I now have minus 3/2 minus lambda minus 3/2 minus lambda x sub 2. There's the x sub 1 getting removed, minus 1/4 x sub 2, and that equals 0. Or if I factor all of those coefficients together, I now have a minus 3/2 minus lambda squared minus 1/4 all times x sub 2 is equal to 0. And I'm trying to find a real value or real values for lambda that allow this equation to be true or valid. Or is there a real number lambda such that coefficient that precedes or scales x sub 2 equal to 0? Can I find real numbers lambda? And this is now a quadratic, isn't it? It's lambda squared. It's quadratic in lambda. We have a lambda squared if we multiplied all of that out. And if we did, we could say, oh, we have a quadratic equation, and we can solve that and see if we get real roots. Or we could just set that equation equal to 0, and we see that we have minus 3/2 minus lambda squared equal to 1/4. But that's just saying if I take the square root of both sides, I now have minus 3/2 minus lambda is equal to plus and minus the square root of 1/4, which is 1/2. And now I can say lambda is actually equal to minus 3/2 plus or minus 1/2, or it's minus 1 or minus 2. And those are both real, aren't they? So in this case, that matrix now has two values of lambda that are real that will satisfy that ax equal lambda x. That's how we set it up. And the lambdas now are eigenvalues, and they're real eigenvalues. What are the eigenvectors? Are they the x and y axis? Well, now we know what values we can use for lambda. Why don't we plug those back into this A and the line above B? We now have an equation for x1 and x2. Those are our coefficients, or our coordinates of our eigenvectors in the formulation, x1 and x2. And we now have two possibilities for lambda. If we plugged in one value of lambda, we should get two equations in these two unknowns, x1 and x2. And we should be able to solve for x1 and x2 to find the coordinates of our eigenvector associated with each of those two eigenvalues. Let's do that. Let's find our eigenvectors then for this example. And this is maybe different from the way that you've used eigenvalues and eigenvectors before. Before, maybe you found a determinant. But in this book, Linear Algebra Done Right, determinants aren't introduced until the last chapter. So we can't use determinants. That's why we're doing it this way. We're trying to think about this differently. And let's see what that means when we start looking at these eigenvectors. Our first equation was this minus 3/2 minus lambda x1 minus 1/4 x2 equaling 0. And our second equation was minus x1 plus a minus 3/2 minus lambda x sub 2 equal to 0. Well, that's begging to be put into a matrix structure, isn't it? With x1 and x2 on the right as a vector multiplying a matrix. Meaning, I can now say that I have a minus 3/2 minus lambda and a minus 1/4 x1, x2 equaling 0. And that's the first equation. The second equation can go in the second row, and that's a minus 1, and I now have a minus 3/2 minus lambda, 0. And now what do we have? We really have an operator that operates on a vector that gets mapped into the 0 vector. What did we call such vectors? Or where did those vectors live? They're in the null space of that operator, aren't they? So this vector, which is really a parameterized form of an eigenvector, it has to live in the null space of this operator, since it's mapping some maybe non-trivial vector into the zero vector in our output space. So this matrix now, when we plug in the appropriate lambdas, better produce a null space that this eigenvector can live in. That's the plan. This vector now, x, is in the null space of, did I start with this matrix? Yes, I called it a B, didn't I? So now I can say that B matrix minus lambda I. That's really what this is, isn't it? This is B minus lambda times I, the identity matrix. That's another way of thinking about what we've just done or indicated. Or we could say X is an element of the null space of this matrix B minus lambda I. We can now look at what that results in when we plug in specific values for our eigenvalues. And our eigenvalues we just determined, didn't we? And they were real, -1 and -2. Let's see what happens when we choose lambda sub 1 equal to -1. We can plug in that value of lambda into our matrix B minus lambda I. The 1, 1 entry becomes -3/2 plus 1 -1/2. You need to keep me awake. I may fall asleep here. What else do we have? Oh, I can do the next one. -1/4. I had to substitute in the correct lambda, right? That, oh, and I can do the next one. So I did half the problem. You guys need to do the second half. So now the last fourth of the problem is I just need to replace this lambda with exactly the same lambda 1 that I used before. I now have -3/2 plus 1. That gives me another -1/2. Is that right? Did I do something wrong? I told you you guys needed to keep me awake. So I now have -3/2 minus a -1. Is that okay? So now I have -1/2 plus 1. So I'm sorry, a -3/2 plus 1. Well, I'm not saying it right. To end up with a -1/2. And that's supposed to equal 0. Now for a linear combination of columns to give me the 0 vector, what do I need to know is true about those columns? If I can add a linear combination of those columns that put me into the 0 vector, what do I know about those two columns? In this case, it's 2. Can I say anything about the relationship of these columns, or can you even see it? And now I'm wanting to fill in a blank, and I want this blank to be one of two words. And I'm trying to remember what chapter. I think this is chapter 2 where we were talking about, pardon? Dependent. Yes. So these columns are dependent, aren't they? Because they're related by a scalar. You can find a scalar that makes those the same. So these columns are dependent. And because they are dependent, that means that that matrix made up of dependent columns has a non-trivial null space. We can find a linear combination, and we can find an x1 and an x2 that can combine those two columns to give us the 0 vector. Our null space is non-trivial. See how we can play with all these previous chapter results? Talking about null space, linear dependent, independent, zero vector, input vector, output vector. All right, so now we have these columns that are linearly independent, linearly dependent. I told you need to keep me awake. Wow. And you have a hard job because there's still a few minutes left. We can now just select one of these. Suppose we choose x1 to be 1. Then if I look at the bottom row, I can use either the top row or the bottom row. If I choose the bottom row, I now have minus 1 minus 1/2 x sub 2 equals 0. I just substituted x1 equal to 1 into the bottom row. And if I scale this up and solve for x sub 2, or if I replace x sub 2 with minus 2, I better get 0, which says now that my eigenvector for a value of lambda 1 equal to minus 1, what's that eigenvector look like? Well, I said x1 to 1, that gave me that forced x2 to be minus 2. That's now an eigenvector associated with lambda sub 1 equal to minus 1 for this matrix B. What if we did the same thing for the eigenvalue minus 2? If we plug that value into that same matrix, we end up with 1/2 minus 1/4 minus 1 and 1/2. We better have some dependency among those columns if we want a non-trivial vector in the null space of that matrix. And they are. You could multiply by minus 1/2 if you wanted to and get the second column from the first column. We need to find x's, don't we? So again, let's just let x1 equal 1. And again, with the bottom row, we have minus 1 plus 1/2 x sub 2 equaling 0. Or now x sub 2 is equal to 2. And our eigenvector, let me just call it x hat instead of x bar. It's something different than the previous one. This is now 1, 2. And that's different than 1 minus 2, isn't it? So we now have two eigenvectors, each one associated with a separate eigenvalue. Questions on example 3? Like I said, I was having too much fun with examples. What do you think? Have to have another one, don't I? No, I can't take a question. I'm too worried about my examples. Yes, question? So the question was, why did we pick x1 equal to 1? Because I thought that would make my life easier. You can choose x sub 2 equal to 1 and solve for x1. You just need to find two values for x1 and x2 that satisfy that equation. And as long as you do that, you're okay. That will give you a legitimate eigenvector. And if in that case you chose x2 equal to 1, then what would you have for x sub 1? If x sub 2 was 1, x sub 1 is going to be a half in the x hat vector. It's just a scaled version of that eigenvector that I derived. Other questions? Okay, good. I was getting nervous. I needed to get on to this next example, right? All right. We started with A1, went to A2. We did a B. Let's try C. What about C equal to minus 1, 2, minus 2, minus 1? Does it have real eigenvalues? And if you've had any linear algebra, maybe you can already answer that question. Or if you've taken some of my undergraduate classes, maybe you remember that that structure is screaming at you in terms of what its eigenvalues are. Maybe not. Let's see what we can find out. We can just do the same approach that we tried before. We need that equation to be true. Our eigenvalue-eigenvector equation, which says that I could write this as C minus lambda times the identity matrix times X is equal to 0. Or since that's 0, I can multiply by minus 1 without really changing anything, which is lambda I minus C is equal to 0. And sometimes it's easier to have your lambdas with positive coefficients than being subtracting with lambdas. It gives you the same relationships. Whoops. I told you. What am I missing? I can multiply by minus 1, but I can't remove an x, can I? Without doing something a little bit more interesting than what I did. So there's lambda I minus c x is equal to 0. If that's the case and c is right there, then that should tell me that I have lambda minus c, which gives me in the 1, 1 entry lambda plus 1. In the 2, 2 entry, I also have lambda plus 1. And now I don't have to worry about any more lambdas because they were just on the diagonal. And I need to just change the sign of my off-diagonal entries in C since I was subtracting C. And that now needs to be operating on a vector, x1, x2, to give me the 0 vector. And I'm trying to find real values for lambda that satisfy this set of equations. So if I look at the top row, I have lambda plus 1 x1 minus 2x sub 2 equals 0. In the bottom row, I have 2x1 plus lambda plus 1 x sub 2 equaling 0. And if I sort of do the same approach that I did before, if I solve this bottom one for x1, I see that that produces this relationship between x1 and x2. And if I now plug that back into the first equation, I now have minus 1/2 lambda plus 1 times lambda plus 1 x sub 2 minus 2x sub 2 equaling 0. I don't really like to have fractions. So let me multiply, and I don't like those negative signs. I'm not changing anything if I multiply both sides by 2, which gives me then lambda plus 1 squared x sub 2 plus 4x sub 2 is equal to 0. But that's just lambda plus 1 squared plus 4 x sub 2 equal to 0. And now I can answer my question. Is there a real value for lambda such that lambda plus 1 squared plus 4 is equal to 0? Can I find a real number lambda that will cause that to vanish? And I can't, can I? Because it's always non-negative, that particular expression. The answer is no. Lambda plus 1 squared plus 4 is actually always bigger than 4, isn't it? Which is bigger than 0. Pictorially, that's just this. The minimum value is at lambda equal minus 1, but then it just grows, doesn't it? If we looked at it. There's no real value of lambda that causes this function to equal 0. So I could have had a couple of roots or no roots for this quadratic. A couple of real roots. In this case, I didn't have any, did I? Well, what are the roots of that? How come this is not working the way the last examples worked? This you learned in 3rd grade, didn't you? Probably, how to solve the quadratic formula. Teasing a little bit, but somewhere in your earlier educational process, you learned the quadratic formula. If we did it like we did it last time, if we just say, well, this is lambda plus 1 squared equaling minus 4, ooh, that's looking a little ornery. But I can take the square root of a negative number by introducing this j term, so that I now have plus and minus j2, which says then that the roots needed to satisfy that quadratic are actually complex. And so if I was living in the field of f being complex, then I would have eigenvalues. But if I restrict my case or my field of numbers to be real, that matrix doesn't have any eigenvalues that are real. But these are minus 1 plus and minus j2, which are in C. And do you remember what the matrix looks like or looked like? C equaling minus 1, 2, minus 2, minus 1. Now do you see where those eigenvalues are screaming at you? The real part of your eigenvalues are on the diagonal, and these off diagonals were equal, opposite sign, and that gives you your imaginary part of your eigenvalue. And if you have that structure in a 2 by 2 submatrix that's a diagonal, a block diagonal, or a block upper triangular, or a block lower triangular, we'll maybe make that more clear later. With one of those blocks looking like this, you know that you have the eigenvalues in that little subblock are minus 1 plus and minus j2. And you won't have real roots. C equaling this has no real eigenvalues. Questions on those examples? All right, now it's back to the book. Let's formalize what we've been talking about, but I'm hoping now that you have a better feel for what can happen when we start talking about invariant subspaces, fields of real numbers, fields of complex numbers. Now when you're reading the book, hopefully it will start to make sense, or if it doesn't, you can go back and say, how does this connect to these examples that he just talked about? Where are these examples and how do they fit into what I'm reading? That's what I'm hoping you can do now. But now we can go back and we can say, let's formalize what we've just talked about, or this development of the concept of eigenvalues and eigenvectors, which really means let's go back to the book, chapter 5. And in chapter 5 now we are focusing our attention on operators. And now you could, if you needed something to think about, you go, oh, that's a square matrix. If you needed a one representation of a operator. Operators in general just say the input space is the same as the output space, and your operator is moving you between that same space, from the input space to the output space, but those two spaces are the same. That's when we can use this term operator. Now, what we're going to assume also is this vector space V where we're living. That's the input and the output vector space. We're assuming V is always a non-zero. So we're avoiding the trivial case where it might just be the zero vector, the zero. So we're assuming V is always a non-zero finite dimensional vector space. But we are allowing for either the field to be real or complex over F. And with that, we can get into the heart of the class. Which is really, we're trying to understand what happens, or the structure of linear operators. And if we don't have those representing a matrix, then we're just talking about these linear operators T living in this set or this vector space of linear operators on a vector space V. Now, those eigenvectors those were kind of neat. They had special properties, didn't they, with respect to these operators. If we hit them with an operator, we went right back onto that eigenvector. That was kind of nice. Well, now we can sort of talk about that relative to some terms that we've already used, and that is to try to break up this vector space V into smaller pieces. And remember how we did that in an earlier chapter? We had direct sum combinations of subspaces to create a vector space V. Now, a useful place to start then with these linear operators is by considering our vector space, which is this capital V, as being dividable or represented as having a direct sum decomposition. Meaning V might be a bunch of subspaces parameterized by the U's. U1, U2, up to U sub n. What does that mean? That is, every element in V. Every element means every vector in V, in our vector space V, has a unique, that's the nice thing about this direct sum decomposition, has a unique decomposition in terms of elements of the various subspaces. One thing we do know about these vector spaces is that we can at least find a simple decomposition, or the trivial decomposition. Every vector space has a decomposition let's say like this direct sum decomposition. But in some cases, or although, it might be the trivial decomposition, which V is then equal to itself plus the zero vector. That is a direct sum decomposition of a vector space. Now that we have V split, broken apart, now since we have split V, into this direct sum decomposition into non-overlapping subspaces, they do overlap at one point, don't they? All subspaces have to contain this zero element, except for 0, since all, let's say these subspaces contain 0. We can think of these linear operators T as acting on each of the subspaces independently. And now you can sort of see what that might be. If these subspaces were these maybe vectors defined by our eigenvectors, then we could think of that operator operating on each of those eigenvectors. And if we know how each of those eigenvectors are mapped, which we do, they just go back on themselves, we can now rewrite any element or vector we want in V in terms of this eigenvector sort of basis set. But we haven't gotten there yet as we're going through chapter 5. We now are just thinking that way. In the book, the author, Axler, actually uses the following notation to indicate that we're restricting attention to one of these subspaces. The linear operator T, vertical line, let's say U sub j. which really is a way of denoting that T is restricted to the subspace U sub j. That's what we're meaning by that notation. T restricted to U sub j. And we'll use that. Now that I've already shown you examples where we know how that works, this is not guaranteed to work in general for a generic subspace that we've parameterized our vector space V into. That's what I'm going to try to say now. Unfortunately, this restriction, or unfortunately this isn't as helpful as we might hope, since there is no guarantee that T restricted to U sub j is an operator on U sub j. i.e., the linear operator T might actually map some vectors to other subspaces, meaning we may pick a vector in a subspace, a U, operate on it with T, and it doesn't stay in that subspace. We've learned that eigenvectors allow that to happen, but if our parameterization was in subspaces that weren't along our eigenvectors, that's not guaranteed to happen or to be true. Here's an example for that. Yes? Really? Sorry for that interruption. Hopefully you didn't even notice if you were watching the video. Here, let's consider the following. Suppose that we're working in this three-dimensional space, and we let U1 equal the x-axis, U2 is the y-axis, and U sub 3 is the z-axis. So that V is now U1 plus U sub 2 plus U sub 3. Since we can write any vector in terms of x, y, and z coordinates. So V is U1 plus, that's a direct sum of U1, U2, U3, since any vector in V can be written uniquely as V is equal to U plus, let's say V plus W. That's kind of a bad way of doing it, isn't it? Let me say V1. So V1 is equal to U plus V plus W. And now with, let's say, U an element of U1, V an element of U2, and W an element of U sub 3. Now what I want you to consider the following map. Suppose you take some vector in 3 space, and that now actually just rotates 90 degrees. in the xy plane. So we take, and that's not what I wanted to do here, take the y coordinate and rotate that, I'm sorry, take the x coordinate and rotate that into the minus y axis, take the y coordinate, put that into the y axis, and now z. That's a 90-degree rotation in the xy plane. What happens if we say t restricted to u1? Consider that. And one example might be, suppose we operate on something on the x-axis with this linear map. Where does that go? What's the output of 3, 0, 0 through that linear map t? We take y, and that's going to be negated and put in x. We take x and put that in y, and we just copy down z. And is that vector 0, 3, 0 in u sub 1? U sub 1 was the x-axis. It isn't, is it? So we're not guaranteed of always finding these nice subspaces which, when operated on by a linear operator, get mapped back into those subspaces. When it does, those subspaces are invariant with respect to the map, and we've just seen that eigenvectors are invariant subspaces. We'll pick up at that point on Monday. But hopefully you'll have